Hi, everyone. I will present you a bit about the experimental rock deformation across the scale. And so basically it's how we squash rock across the scale between time and space. So moving on to the next slide. So as you know very well, we see deformation patterns at all scales, and I'm talking about both time and space. So if we first look at space, we see them under the microscope. We see them when we pick a sample being out from an outcrop, or when we bring it back into the lab, but also obviously when we just simply look at outside in our landscape at all scale again, as we have also patterns that we can only see from satellite view, for instance. And when we see that, we know it happened. It's something that happened in the past, and we see something that is done, or at least at a certain stopped time. And in fact, these had happened either very quickly, perhaps even through just nanoseconds, especially for crack formation. It can be very sudden, but other patterns took like a million years to happen. And the type of deformation also span a great range of features, being what we call brittle, which is a physical separation of pieces, or also ductile, which is what we gently say is just as playing with Play-Doh. So, but it's a bit more difficult to do that with rocks. So the way we approach it from the lab has been derived from solid material science first. It started quite early in 1910 with von Karman being the first recorded apparatus developed for the rock deformation using hydrostatic pressure. And then it's been picked upon and improved by Griggs, who is Dave Griggs, who is a very famous name in our field. But again, no visual record of those yet. And it's only in the 50s when Hendon and Hurd, working at Shell in Texas, who developed the technology further, also started to have a camera to take pictures about it. And so this is the little images that you can see on the screen from these early on apparatuses. And then moving on, these apparatuses that allow us to deform rock and try to mimic what we can see has been further improved by Patterson in particular in Australia. And this is quite an important step because he was the first to be able to set up a company out of that and make a business for that. And so introduced a form of standardization for rock mechanic testing. Obviously, it didn't stop there, and we still have plenty of bespoke apparatuses, but at least this has formed certainly a very strong foundation for developing similar tests across the different laboratories. Now, if we look at what we look, so from the spatial scale, we work for over lots of scales. So typically between microns and decimeters in terms of sample scales that we look at in the laboratory. To do that, we use dedicated apparatuses that have specific environmental condition. And we obviously need, as we're in the laboratory, to simplify the natural condition by necessity, either by focusing on a homogeneous material, which is, as you know very well, unlikely to be a real case in natural, in any field work. Or we tend to control the distribution of the mineral we're ingested and so on. And this is also to be able to better interpret the result that we're drawing from these tests. And as mentioned by Stefan Stock before, this also tends to define one's lab identity, so that we have many labs that have different apparatuses also because they are focusing on different aspects of what we can study from experimental rock deformation. The temporal side in rock deformation is approach in the way we perform the test, how the procedure is being designed. We integrate the time either by performing time series tests or by varying strain rate, for instance. from instantaneous shock to creep rate, like very, very slow deformation. In any cases, the time will be faster than the natural processes by necessity. And so again, what we would work could be from having seen something in the field, wanted to understand what happens. So we will design a test, select the kind of apparatus that can help us achieving the experiment that we need. And then once we get the result, then we will put them back into a model that we will test again the observation and see if we've captured what we wanted to see or no. But I've on purpose put a look, because sometimes things goes simply just around the loop or just moving things around. We may have a model that tend to point to something. We need to see, do we have the field interpretation and how was this achieved, and so on and so on. Now, getting back to these patterns, what is interesting here is that I've highlighted two boxes, and these boxes are bracketing what is here identified as the state-of-the-art rock deformation laboratory. So basically, a rock deformation laboratory will have something that is able to handle samples that are from a few millimeters to just about 10 centimeter, and will be able to reproduce that kind of deformation. And now also new type of deformation apparatuses are also coupled to X-ray microtomography. And so they also are able to take images of the deformation going on. However, this is only happening on smaller scale samples. So in order to achieve high resolution imaging, we need to get smaller sample. These constrain also the type of material that can be tested, as I will explain a bit more later on why. So now that we focus on the sample, here is just a series of samples that I'm familiar working with. It might seem nothing, it might seem quite a huge scale. So basically, the smallest sample on the left here is a 5 millimeter diameter cylinder by about 1 centimeter length. This was done for doing one of these X-ray synchrotron microtomography couple tests. And on the opposite side is the biggest sample I ever had to deal with. And it's 10 centimeter, sorry, diameter sample by 25 centimeter in length. And this is one of the biggest sample that we tend to have in a rock deformation lab in general. And the reason for having this kind of size variation is not only due to the apparatus and sensors that we are looking at using, but there is also a necessity. The geometry here is a cylinder, a right cylinder. It's very typical, but it's not the only one. We can also work on a rectangular prism. But what is important is to make sure that we have enough material representative within that geometry, so that the geometry will not constrain what we're looking at imaging or measuring, the type of deformation we're looking at. And the cylinders appear as one of the most ideal geometry to achieve that. And we have to make sure that we have enough mineral within our geometry, so that we're not having any effect from that. So for instance, when you're looking at deforming rock like halides, which tend to have big crystals, then you really need to produce quite large sample to be able to offset any effect of these minerals. Other material with very small grains do not have this issue, therefore we can study them at very small scale as well. Showing here on the bigger scale the type of sample that we can get. We can have super large cube or prism. This is particularly true from true triaxial compression tests and torsion tests that exist. And on the other side, we move from rock physics to mineral physics when we're looking at deforming material that is smaller than millimeter, just a few micron. And this is when we focus from a rock, which is a composition of several minerals to just having just one kind of mineral, or just one mineral from crystal, in fact. And so we look at other apparatuses for doing that. Of course, we just don't do any just solid material. We also look at powders to try to see what is fold gouge material behavior, for instance. And we can do that in different apparatuses, as the one on the top, which is just two L-shaped sliding, or as the video at the bottom show you when we try to reproduce the speed of fold movements and the friction that results out of it. This is a very small sample of various apparatuses that are available across the world, and of course within EPOS MSL as well. So we have a simple test which is performed using a uniaxial comparative strength apparatus, which is shown here on the top left. And then at the center, we have a triaxial apparatuses which reproduce the same kind of principle, but adding a confining medium around the sample. And these are quite standard. At the bottom center, we have a shear apparatus where the sample are two blocks hold against each other, and then one is sheared while the other one is held in place. And then we have other interesting apparatuses, but are more one of a kind. The yellow frame is a torsion apparatuses that is definitely one of a kind. So that's as to be able to twist a sample and see how it folds this way. Then we have on the bottom left a way to also twist the sample, but this time to a very, very small scale with a sample that is just 1 centimeter large, basically. And then on the bottom right, you have also another kind of apparatus that is very interesting because the time scale here is very quick, as it's a shock apparatus. So basically a piece of rock is just like projected as just a bullet to see the impact and a rapid shock effect on rock formation. So here, as I mentioned, we can achieve different results. And so I'm putting here images of this different way of deforming the sample. So typical brittle failure when we look at how rock cracks. And then moving on, adding pressure, we can still have really nice fold here. But then also we can start to combine the different mechanism and achieve more complex deformation, if one can say so. And like I mentioned before, there is this one kind of apparatus that also is very dedicated to one particular kind of deformation, which is torsion. And now, over the past couple of decades, yes, because it really started that nice. Oh, please, where I'm back. Come on. Okay, hopefully I'm back. Sorry about that.
Seems to be okay.
Yeah, you hear me well now?
Yes, I can hear you. Thank you.
Sorry about that. So as we are always interested to gain more and more insightful knowledge of what's going on during deformation, we've tried not only to reproduce the existing mechanism, but also image them as they happen, basically, instead of being again blind, because we see things in nature as they happen. And till now, we were most of the time also seeing our sample deform afterwards. Although we knew how we had achieved it, it's quite different to be able to see it as well. And this is now possible having little machines that are capable of the same capacity of deformation now, but also coupled to X-ray synchrotron microtomography. I've put here 2 of them, but they're not the only one. And one is linked to the European synchrotron facility, in France, and is capable of very similar deformation that you would have in any state-of-the-art rock deformation lab. Another one is just about the same capacity as well, but as the capacity also to be able to be moved around any synchrotron. So as these are not project where I'm deeply involved, I will just let you know to discover more following the link that I've provided. And I will simply move on to the fact that to the smallest scale that we can achieve is between rock deformation and mineral deformation. And so again, this is really on the frontier of the field, but it's very interesting as well. And this is where we move on really deeper into the earth in terms of environmental reproduced in the lab, but we also move a lot smaller as well in the sample scale, as we are going to just micron to millimeter. That said, we have all this facility pretty much available in Europe, although a few of them are not yet here on our continent. Lots of them are available across Europe. And among those one on the map on the right are the one that are already accessible via the EPOS MSL transnational access. All the other, I'm sure, will be also welcome to have direct contact from anyone, and maybe just are willing to join us. And that will be it for me. Thanks for listening.